Welcome to our DfMA analysis of a mini blender. Presenting today are Lauren, Lily, Arthur, Nick, and Alexandra. We will be presenting the full contents of our final design report. A mini blender is a small and portable kitchen appliance used to chop, mix, and puree ingredients. The primary customer is home consumers, and the secondary is health and fitness buffs. Our total production volume is 150,000 blenders at 50,000 per year with a 3-year payback period. 75% of these blenders are bought by primary customers and 25% by secondary. This is the exploded view of our mini blender with 14 parts.
A fast diagram was created for the mini blender. The task function is to blend food. The primary basic functions are to chop food, mix ingredients, and store liquid, which were broken up into 7 basic functions. Also, the blender should assure dependability, assure convenience, enhance product, and please senses. 2 of these were broken up into supporting functions. Our first feasible assembly sequence is bottom up, starting with the base rubber and ending with the cap and handle. Our second feasible assembly sequence is top down, which starts with the handle and ends with the base bottom and base rubber. The 2 assembly sequences were compared against the following criterion. The bottom-up assembly scored higher overall, as it is easier to locate parts and fasten and join parts.
This is our function component mapping matrix. This is our bill of materials, and we modified it to include the second blade piece, and the total cost is $25.17. Our rough cost estimate was about 50% of the retail price of $49.95. This is our quad chart, and the high manufacturing cost and high functional importance parts are the motor, the blade pieces, the body, and the blade stem.
This is our functional differentiation table, and the functions that were different for each customer group were cut strips and allow portability. This is our component commonality table, and our modules are the handle and the blade piece.
Our first product variant focuses on the blade and stem module, which blends the user's food. To offer more viability for our secondary customers, we created a new blade called a Julienne disc. To maintain a common interface between the original and modified parts, I produced an identical pill-shaped hole or slot in the disc for a simple replacement of parts on the stem. The next product variant is the cap and handle module, which prevents leaks of the blender's contents. We modified this module for portability for customers on the go. To maintain common interfaces, the clip connector has the identical pill-shaped boss of the original handle component.
This is our bottom-up assembly sequence. This is our modified assembly sequence with delayed differentiation, allowing for the rubber body seal step to be before the blade piece 1 or Julienne disc step.
For design for manual assembly, the assembly analysis gave us a total assembly time of 60.65 seconds and a theoretical minimum number of parts of 10, and the efficiency was 0.495. The platform part is the blade stem, and the module parts are the blade pieces. Because they have high manufacturing cost and high functional importance, we chose them for the redesign for manual assembly. DFA2 reduced fasteners was changing it to press fit instead of riveted. DFA10 was filleting the top of the blade stem for easier insertion, and DFA6 was increasing part symmetry of the blade stem so that it's square instead of pill-shaped, and DFA1 was reducing the part count by combining the blade pieces into one, and DFA8 was redesigning the blade piece so that it's bent from sheet metal instead of machined from a solid to avoid nesting. Redesigned parts for manual assembly improved the total assembly time to 50.75 seconds and the efficiency to 0.591. The manufacturing cost would be lower because the blade stem has a rounded square shape instead of a pill shape, and the blade piece is made from simply bent sheet metal instead of a round-edged machine piece.
Here we have our design for automated assembly cost analysis. Based on the geometry of the parts, 5-digit handling codes and 2-digit insertion codes were assigned. Our 14 parts thus had a total assembly cost of 73.26 cents, with 4 of the parts requiring manual assembly. The blade subsystem was selected for automated assembly redesign, as their total assembly cost of 25.74 cents made up 35.14% of the total cost, and their high functional importance made the parts good candidates based on the quad chart for DfMA. The blade bushing was redesigned first to increase part symmetry by removing an unnecessary diameter step down, removing the need for end-to-end orientation, and making the part more standardized. The blade stem was further modified from design for manual assembly by adding chamfers to inserted surfaces and changing the square-shaped peg to a threaded screw, removing the need to orient on the principal axis. A potential drawback is that this would require a different motor connection and necessitate a specific rotational direction while blending to prevent the stem from unscrewing itself. The blade redesign is very similar to that in design for manual assembly, with the exception that the riveting process was maintained due to having a lower cost for handling than the press-fit process suggested for manual assembly. Other benefits, such as avoiding tangling and nesting and reducing the part count, are from DfMA. Together, these modifications reduced assembly cost by 10.62 cents, bringing the total to 62.64 cents. These savings would greatly increase with the higher production volume, as the modifications made significantly increased max feed rate, but didn't affect handling costs due to the low production volume need.
For the process selection, we chose to analyze the 2 parts from the redesign for automated assembly, the blade piece and the blade bushing. The key dimensions for both parts can be seen in the figures below. The blade piece is made from stainless steel and the bushing is made out of ABS. The critical functions for the blade piece are to break chunks, slice fibers, cut strips, stir contents, and lift liquid. The critical functions for the blade bushing are to prevent leaks and protect electronics. First, the possible manufacturing processes were filtered by material. The blade piece is made out of stainless steel, which is a ferrous metal. The manufacturing processes available for ferrous metals are sand casting, investment casting, centrifugal casting, forging, sheet metal working, powder methods, electromachining, conventional machining, and additive manufacturing. The blade bushing is made out of ABS, which is a thermoplastic. The processes available for thermoplastics are machining, injection molding, blow molding, compression molding, rotational molding, thermoforming, and additive manufacturing. These manufacturing processes were then filtered based on the part shape. The shape of the blade piece is sheet, flat, or folded. This shape eliminated sand casting, investment casting, centrifugal casting, forging, and powder methods. The shape for the blade bushing is prismatic and circular. This shape eliminates blow molding, compression molding, rotational molding, and thermoforming. Next, the processes left were filtered against the mass and section thickness of the parts. The mass of the blade piece is 3.3 grams, and the minimum section thickness is 0.76 millimeters. The low mass of the part eliminated electromachining from the possible processes. The blade bushing is 0.1 grams, and the minimum section thickness is 1 millimeter, so no processes were eliminated. The remaining processes were then filtered against the tolerance and surface roughness of the parts. The blade has an upper tolerance of 0.5 millimeters and a surface roughness of 0.5 microns. The small tolerance and surface roughness are required as the blade piece is a press fit into the blade stem and the blade is used to cut food for the users. These parameters eliminated conventional machining from the possible processes. Similarly, the blade bushing also had an upper tolerance of 0.5 and a surface roughness of 0.5 microns, as the blade bushing fits snug to the blade stem and acts as a seal to protect electronics. As a result, conventional machining was also eliminated. Lastly, the remaining processes were filtered against the economic batch size, which is 150,000 for both the blade piece and the blade bushing, since there is one in each mini blender. The relatively large batch size eliminated additive manufacturing for both parts. A process selection table was created to summarize the results. The chosen manufacturing process for the blade piece is sheet metal forming, and the chosen manufacturing process for the blade bushing is injection molding.
And here you can see the blade bushing cost analysis before design for manufacturing modifications, where the total cost comes to $0.07043 per part. This is our blade bushing redesign, and on the left you can see the original part, and then on the right you can see the modified bushing before being put into DfM Pro. So the two changes that were made were, one, changing the material to a lower cost material, which is in this case was from ABS to high density polyethylene, and then two, we removed unnecessary material and added ribbing to compensate for the removed material, and then both of these changes correspond with DFIM 1, which is minimizing wall thickness. The design was then put into DfM Pro, as you can see on the left, where then it was suggested that we add fillets, which you can see on the picture on the right. This change corresponds with DFIM 4, which is to avoid sharp corners that are stress concentrators. But after modifications, you can see that the cost to injection mold actually increased, even though the material cost decreased by a factor of around 10. And this is due to increased complexity in the part that resulted in a higher operating and mold cost per part, and the fact that material cost is not a big factor in the overall cost due to the part being very small to begin with. And the redesign should not impact product function or assembly cost, as the functional geometry has not changed.
Next, we estimated the cost of the redesigned blade piece for automated sheet metal working. By calculating the material, operating, and die costs, we found the manufacturing cost of each blade to be 16.84 cents. DfM Pro suggested two ways to improve this original design. First, we applied DFSM 2 to minimize setups by only bending in one direction. Secondly, we applied DFSM 8 to avoid sharp ends. We increased the bend radius to 2 millimeters to meet the minimum bend radius requirements for sheet metal working. On top of DfM Pro modifications, I also changed the geometry of the flanges on each blade to be one smooth triangle. This satisfies both DFSM 6 and 3, in which unnecessary sharp corners are eliminated, as well as improved shape for nesting parts closely on the stock material. Applying the same analytical method for this redesigned piece, the new cost decreases to 14.17 cents per part. Simplifying the geometry reduced material cost. Reducing the number of bends slightly reduced the operation and die cost, but since the opposite bends enhance product functionality, further testing may be required to weigh customer response to this change versus the cost benefits. As you can see in the table, the analytical method of cost estimation is consistently greater than the Hub's estimation, extrapolated to 150,000 parts. Possible reasons for the discrepancies could be tooling, packaging, and labor costs from Hub's estimations.
Our product service system is called Rent-A-Blender, where we partner with popular grocery stores to rent mini blenders. The low-cost rental to consumers will be less than the cost of the blender, and customers will pay at a kiosk before it is given to them. Customers register their name and information to rent a blender at the kiosk, and they can rent up to one blender at 1 week increments. No registration is required, and customers can walk up to the stand at any time during grocery store business hours to rent the blender. Also, mini blender drop-off is at the same location. No additional vehicles are required, as the mini blender is small and lightweight, so customers can place them in the cart and take them home in their car. We would locate rental stands near produce, which gives customers access to fruits and vegetables to make smoothies, and the shared blender usage reduces waste from many individuals owning their own blenders.
Our work in DFA and DFM results in lower manufacturing costs that can be passed on to customers in a lower total blender cost. This also increased production efficiency, which could allow greater sales volume. Our design is excellent for affordability, but could be lacking in longevity, functionality, and performance. If we were to do this project again, we'd probably pick a different product with more parts and more part variety, meaning more metal and plastic pieces that could be analyzed for DFA and DFM if we were to start over.